Welcome to this explainer. Today, we're diving into the absolute classic n-queens coding problem. And honestly, we're going to break it down like a strategy game. If you've ever wondered how computers elegantly solve complex constraint problems, well, you're in the exact right place. It's not just a puzzle, it's practically a rite of passage in algorithmic thinking. So here's the massive question. How do you fit n-queens on a board without starting a royal rumble? It's a fantastic puzzle. To actually solve it programmatically, we have to find the exact number of distinct configurations where absolutely no two queens can attack each other on an n-by-n chessboard. Now, I know that sounds super simple on the surface, but trust me, as that board grows, the mathematical complexity just absolutely explodes. Here's our roadmap for the explainer. We'll start with the n-queens challenge, look at queen movement constraints, dig into the backtracking strategy, figure out detecting attacked squares, and finally, wrap up with time and space complexity.
All right, Section 1, the n-queens challenge. Let's visualize the goal. This really brilliantly illustrates what we're aiming for. Look at a standard 4x4 grid, where n equals 4. There are literally only two exact ways to place 4 queens safely. See how the queens are staggered, completely avoiding each other's line of sight. So our algorithm needs to systematically find both of these valid configurations, and it has to do it without missing a single one or, getting trapped in some endless loop. Moving on to Section 2, Queen Movement Constraints. These are our rules of engagement.
The queen is without a doubt the most powerful piece on the board. She strikes in 8 different directions, vertically, horizontally, and diagonally right across the entire grid. Because of that, our placement strategy has to be incredibly careful. Just a single misstep completely invalidates the whole board state.
So here's the absolute crucial point. A square is only safe if it avoids sharing a row, a column, or either diagonal with any existing queen. It's that simple, but also that strict. Our code needs a rock-solid mechanism to constantly enforce these 3 specific rules every single time we even try to drop a new piece onto the board. Okay, Section 3, the backtracking strategy. This is the core engine of our solution. Let's look at the actual logic of our backtracking algorithm. Step 1, we try to place a queen on a brand new row. And we do this row by row, which is a neat little trick to automatically satisfy that no shared row rule. Step 2, we check for attacks using those constraints we just talked about. Step 3, if we hit a dead end, like literally no square is safe on that row, we just retreat. We backtrack and try again. And step 4, repeat. We're just placing one queen at a time, continuously moving forward or backward until every single solution is fully mapped out.
Let's trace this logic in action. Say we place our first queen, and then we confidently move down to the next row to place the second. But wait, every single square is under attack. It's a total dead end. When an entire row is blocked like this, the algorithm forcefully backtracks. We literally pull the previous queen right off the board to test a new position for her. That effectively clears the way so we can find a valid placement and keep moving forward. Now think of this as the algorithm's memory mapped out. It's a partial state space tree for n equals 4. Every single node you see is a different board state. Those paths leading down to a green checkmark, those are our winning solutions. And the paths ending in a red minus sign, total dead ends. The whole process creates this massive decision tree, mapping out every successful placement and, of course, every failed attempt along our entire algorithmic journey. Which brings us to Section 4, detecting attacked squares. Let's look at optimizing with math. So we know we can use hash sets for the columns easily enough, right? Like if column 2 is occupied, just add the number 2 to a hash set. Boom, done. But identifying a specific diagonal line on a grid, that is definitely not that simple. They don't have a nice single index. Figuring out how to efficiently track those diagonals requires a real aha moment of math. Okay, picture a standard coordinate grid. The diagonals go top left to bottom right, and the anti-diagonals run the exact opposite way. Well, the absolute breakthrough revelation here is that every square on a specific diagonal actually shares a unique mathematical ID, and it's based purely on its row and column coordinates. It's kind of like a hidden barcode. Here's how that breakthrough works. By calculating R minus C, so row minus column, we get a constant unchanging ID for the main diagonals. And for the anti-diagonals, we just use R plus C, row plus column. By doing this super simple math, we can instantly drop these IDs into a hash set.
And what does that mean for us? It means that instead of slowly scanning the whole board iteratively, our algorithm just performs an O of 1 lookup. It tracks attacks with absolute lightning speed. Finally, Section 5, Time and Space Complexity. Let's evaluate the cost. The time complexity here actually comes out to O of n factorial. Now, why is that? Well, think about it. For the very first queen, you have n choices. But because each queen you place dramatically reduces the choices for the next one by attacking those squares, the next queen has n minus some number of choices, and so on and so on. So our time complexity grows factorially, which perfectly mirrors that massive branching decision tree we looked at just a minute ago. However, and this is the good news, the space complexity is incredibly efficient. It's just O of n. This is a massive win. It works so well because our recursion depth only needs to go down n levels to place n queens. Plus, remember those brilliant hash sets we made for the columns and diagonals? Yeah, they only ever need to store up to n values at any single time.
So I'm going to leave you with this final thought. If the tiny little 4x4 board results in just 2 solutions, but carries an O of n factorial time cost, what on earth happens to our decision tree when n is 8? Or what if n is 12? Just think about how incredibly rapidly that search space explodes as the board grows. It really leaves you with a much deeper appreciation for algorithmic efficiency, doesn't it? It shows exactly why clever optimizations like those math-based hash sets are absolutely critical. Thanks so much for joining me on this explainer. And hey, keep exploring those algorithms.